exercises here. I've got 2 more exercises. We can do C, Java, translate them if we want to, do whatever we want. Remember that next week is your first exam and the do-over week. So if you have any one hack that you need points back on or whatever, you can go to, we'll post details about it later on, but be fixing those now in preparation for your first exam next week. It'll be on Friday, so late next week. Right, we are on line, so if you have any questions, you can post to Piazza or to the YouTube live stream here. We already wrote a solution to FizzBuzz in which we used a for loop. We already wrote a program to compute a partial harmonic series, right? Now let's do another piece of math here. The arithmetic geometric mean of 2 numbers. So let's look that up on Wikipedia, what that means, right? So everybody understands what the arithmetic mean is, right? If I have 2 numbers, I add them together and then divide by 2 out here, multiply by 1/2. That's the arithmetic mean. But the geometric mean is you multiply them together and then you take the square root. And what the arithmetic geometric mean is that you start doing this over and over and over again until they converge to the same number. So for example, 24 and 6. Here's the example in Wikipedia, right? Here's the arithmetic mean, it's 15. The geometric mean, however, is 12, right? Because 24 times 6, take the square root of that, that's 144, 12 here, right? Those are not the same, 12 and 15. But if you repeat this process over and over again and feed those 2 numbers back into the arithmetic and geometric mean, then you start to get closer and closer to each other. In this case, if we did that 15 and 12, we get 13.5, and the geometric mean is 13.41, which is really, really close to each other, right? Now, if you do this over and over and over again, right, you see that they become super, super close, right? Even after 5 iterations here, they agree out to 20 decimal points or whatever that is, right? And it's that convergence that is defined as the arithmetic geometric mean. Now, for all numbers, it doesn't necessarily converge after a finite number of steps. This could go on forever, and you would never actually they would never actually meet each other, right? They would just converge, get infinitesimally closer, arbitrarily close, but never actually meet, right? So what we want to do is we want to write a loop that is good enough, right? 10 decimal places of agreement, is that good enough? Is 15 decimal places of agreement, is that good enough, right? Et cetera, et cetera. So let's understand this a little bit better by walking through the example here, right? That you compute the arithmetic and geometric mean of the 2 input numbers, and then you have to feed those in to the same process over and over and over again. So what I want to do is I want to start out, and this is a useful exercise to do when you're writing a loop that for a problem that you don't necessarily understand up front, is either whiteboard it or go immediately to your code and start playing around with actual numbers here. So here's our FizzBuzz solution. I'm going to go ahead and get rid of that. Right? Let's go ahead and create 2 numbers, A and B. Right? Should they be integers, by the way? 24 and 6 are integers. That was the example in Wikipedia. But are they always going to be integers? No. So what should we do? Should we use floats? I've been seeing this all over the place. Not necessarily in this class, but in the other class because they're using Zybooks, and Zybooks, for whatever reason, decides to use floats instead. I briefly mentioned floats so that you should be aware of them, but they are only accurate out to 7 decimal places. Right? Doubles, on the other hand, are accurate out to 17 decimals. Right? So I will always be using floats in this course. Right? There are times where a float does make more sense than double. If you don't need that kind of precision and you want it to be slightly faster, right? For example, lots of gaming engines. I'm thinking of Unity right now. Everything is done with respect to floats because you don't need more than 7 decimals of accuracy when all you're at the end of the day, all you're doing is rendering 1 pixel, right? That additional 10 digits of accuracy is not going to change that 1 pixel, right? So 16, a float is good enough for rendering down to the level of a pixel, right? But in this case, we want to do scientific, numbers here, right? And I want more accuracy. Here's the first iteration. Right? So the numbers over here are the arithmetic and geometric mean, A and G. I've already used A and B here, so let's go ahead and rethink that, maybe X and Y. They're the original numbers, right? So the arithmetic mean, right, double A, is going to be X plus Y over 2. Good math? Bad math. Bad math, why? The numerator is not the numerator. There we go. Do we have integer truncation issues here? Should I instead do, say, 0.0? No. Why? Because X and Y are doubles. The addition, the sum of two doubles is a double. And only one of these things needs to be a double. So we're good. The geometric mean, what was that again? The square root of the product, X times Y. There we go. And because we are in C, and we're bringing in the math library to do this, math.h, now we've got square root, okay? That gives me the first arithmetic mean and the first geometric mean. In fact, if we look over here, they're subscripted, 1 and 2, okay? Well, if I'm going to need more variables here, I should probably go ahead and call those 1 and 2. There we go. And here's my second iteration, 2 and 2. But I don't use the original X and Y. What do I use? The new values, A1 plus G1, and A1 times G1. And I could repeat this over and over and over again, right? Let's go with 3 iterations here, 3, 3, 2, 2, right? But this seems rather, dumb to do this when I need a loop anyway, right? This will get me to the point where, in this example, we're in agreement out to 3 decimal places. I'm going to show you that that actually does work, right? That it goes out to 3 decimal places here after 3 iterations. Printf, the AGM of %f and %f is equal to, arithmetic geometric mean is what AGM is, %f and the line, the original X and Y values, and then say A3 and G, and since they're arbitrarily close, A3, G3 are going to be the same thing, right? So GCC demo. What do we need to do when we're using the math library, apparently on VS Code? Ubuntu, actually, -lm. There we go. So 6 and 24, 13.458. Ah, it works, right? There's my test case right there, already written for me, right? 2 input values, 24 and 6, with an expected output value. And I'm able to verify, yes, indeed, that it is correct out to 3 decimal places. So how could I take this first iteration, this second iteration, and this third iteration, and how can I generalize it so that I don't have to copy paste the same code over and over and over again? So let's keep that as a reference, and let's create a loop up here instead. So let's just outline it first of all. Loop. What should my loop be? Compute the next A and G, right? Arithmetic, geometric means, and update some variables to set yourself up for the next iteration. Okay. So help me out. What kind of a loop do you want to use here? A for loop or a while loop? Let's write this out in English. Repeat this process until both A and G are close enough. So repeat this process until. That English should be screaming out to you what kind of loop you want. Am I going to do this 3 times, 5 times, 100 times? Nope. Until, right, some condition is satisfied. So probably it's more natural to use a while loop, right? While A and G are far apart, right? So writing things out in English, that's called pseudo code, right? Fake code. Writing things out temporarily in English is perfectly fine to do this, as long as you go back and you fill in the blanks and translate it to actual code here. Right? So I'll go ahead and leave that for now. Right? Well, A and G, I'm talking about those variables, right? I probably need those variables. Double A and G. There we go. While A and G are far apart. Right? So we know that they're far apart. So I want to compute the next A and G. What could I call those? Well, I could come back here and rename these, right? Current A and current G. And if I did that naming convention, what would I do? Double next A is equal to double next B, or G is equal to. Right? If you wanted to go ahead and you know, call those current arithmetic mean, current geometric mean, that'd be perfectly fine. You're not paying by the characters here, right? So the next A is going to be what? The current A plus the current G divided by 2, right? Making sure that your numerator is your numerator. And the next G is going to be square root of the current A times the current G. There. All right, so I've computed the next ones. Now I need to update some variables to set myself up for the next iteration. So I've got 2 sets of variables here, the current ones, and then these are the next ones, right, down here. But when I advance through this process, what becomes the current? These become the current, right? Do I need these anymore, the old ones? Nope, I could throw those away. So the next ones become the current ones, and I can go ahead and ignore those. So what should I do here? Current A is equal to the next A, and current G is equal to the next G. Tell me about the scope of next A and next G. I declared them inside this while loop. Are they going to be available after the while loop ends here? Nope. So down here, now that I've got this, I'm going to get rid of all the scratch work here. Now that I've got you know, current A, can I use next A here? Nope. I'd have to use current A or current G. Which one should I print as the answer? Is it going to matter? Why? Because we're broken out of the while loop at this point, right? That means that they're close enough. They're close, very close together. Okay? All right, now we need to come back here and fill in this blank. While A and G are far apart, how can I tell if they're far apart? Two numbers, think about the number line, they're really far apart, right? How do I know that this one's way over here and this one's way over here? Their difference, right? Current A minus current G. But be careful, is this A or is this G? Or is this A and this is G? How can I ensure that the distance is going to be the same no matter what? Absolute value. That's not the absolute value. What is the absolute value? ABS. Careful. We'll come back and fix that bug here in a second. While the absolute value, the difference, is greater than some threshold. Some threshold. Dot, dot, dot. Well, what should our threshold be? Are we okay with it being accurate to 1 decimal place? I don't know. Are we okay with it being accurate to 3 decimal places? That's something that we can put into a variable. I'm going to call that variable epsilon, because that's what they use in math. Right? Epsilon or E. Okay. No, that is epsilon. Or what's another one? Whatever. I'm just going to go ahead and use epsilon. 0.0001. There we go. So if it's accurate to within 10, 100, 1,000, 10,000, 1/100,000th of each other, then we will break out of that while loop and simply report the the result here. Okay. So before it was working and we were getting whatever that number was that I just erased, let's see if it works now. 0. I broke it. Let's understand why. Let's start walking through this line by line. In fact, before we start walking through this line by line, what else should I do to check, smell this code? Wall. Okay, nothing shows up there. So there must be something else. There's also another one, I doubt it will come up, but extra. Oh, hey, there we go. So, at least on Ubuntu, GCC, the extra is actually extra. So there is another linter that you can turn on. Don't ask me why, but if I turn on all warnings, that kind of tells me that all warnings are reported. That's not the case, apparently. Extra warnings are not reported, so tell me about them all, and the extra ones. Don't ask me why they did it that way. But one problem here is it's warning me about the use of abs. What's wrong with abs? The absolute value function is assuming that it's an integer, right? But the actual argument is a double. Abs is not abs. Right? What will end up happening here if it's 0.5 and I use abs for integers? Is 0.5 a integer? Nope. So what happens to it? Chop, throw away, truncation, and it becomes 0 immediately. What should I be using instead? And unfortunately, it doesn't suggest what it should be. But if it's fabs, floating point absolute value. Okay. The rest of this is unused command line arguments. Fine, yeah, that's lint. That's a warning, but that's okay, right? That's not dirt. Right. That goes away. Let's see if it works now. A.out. Nope, still 0. That was actually one problem that would have shown up after we fixed this other problem. Let's start walking through it. Variable declarations and initializations, fine. Variable declarations and no initializations. So current A and current G, what values are stored in those variables right now? If I did poor man's debugging, I could print them out, %f and %f, and the line, and current A, current G. Now, the real answer is what? Oh, there we go. Warning, current A, current G is uninitialized. Why didn't you tell me that beforehand? I don't know why that warning was not coming up before. Apparently, using them in the print statement is actually giving me this warning now. Right? But 0 and 0. Right? Now, uninitialized variables in C, what could be in there? 99.9% of the time, it's these zeros. The other 1.1% of the time, or whatever it is it's going to be garbage. Right? It's going to be garbage or dead beef values, whatever. So what should I initialize these to? Question mark, and question mark. Well, let's go back to our whiteboarding process. What are they initialized to before the loop begins? The actual numbers, x and y. Right? Let's go ahead and put that in there. X and y. There. Now they are initialized. I don't need to print that out. GCC. Those warnings go away. And A.out. 458,171. 458,171. If we wanted even more accuracy, we would have to print more decimal places, and it would only be accurate out to 1/100,000th. Yeah.
Can you scroll down to the print statement?
Why did we print current A instead of current G? Why didn't we print both of them? Again, they've converged, right? They've converged to a spot that's good enough, right? All right. Now that we're assured that this works, we get rid of our scratch work, right? That's cruft. If you want to, you can document, put this into a function, which is our next topic, and then document that function by pointing to the Wikipedia page over here, right? Now, is one test case, the one from Wikipedia, is that good enough? Probably not. AGM of 42 and 101. You tell me, Wolfram Alpha. This is me pulling out my calculator to create yet another test case, right? Using an external tool, in this case, Wolfram Alpha. 42 and 21 is going to be 60, that number right there. 42, sorry, not 21. 42 and what was it? 101? There we go. Run that, and I get 68278178. It's up in here. 27817. There. Yep. I'm convinced. We could print out, you know, we could do poor man's debugging if we still we're unsure of if there was a bug or something of what's happening, and we could use poor man's debugging here to print out each iteration of this loop. I'm not going to do that because I'm going to show you a better way later on. Very, very quickly here, since we have time, what changes over here in Java? Math and the print. That's it, right? Math.abs. Right? They don't have a fabs. They have instead three different absolute value functions, all named the same thing. There's only one square root function, and system.out. There we go. Come on. Wow, it's really slow today. We're streaming well. I don't know why it's not, why Eclipse is having a problem here. There we go. I think that's the same number as before. Right. But here, over here, if there were still a problem, and I needed to debug, what would you do? You set a breakpoint, you fire up your debugger, and then you walk through it. Wow. I don't know why it's so choppy, but whatever. Come on. All right, we'll let you think about that. Darn it. All right. Questions on that exercise? Perfect use of a while loop here. Otherwise, let's do some financial stuff. So what did we start out with? We just started out with a toy solution. We did some pure math, some statistics, which is a different type of math. And now we've got something completely not math related, finance, right? Is it still math related? Looks like it to me, right? There was this one year where, you know, I made an extra effort to try to pull in examples and exercises from at least a dozen different disciplines: finance, marketing, civil engineering, mechanical engineering, electrical engineering, right? All these different areas. And I thought I had done an excellent job. And then one student said, "Why are all of our exercises math?" And I was like, well, you and I just reached a realization. What is every single discipline about at this core? Math. Why? Because math is the ultimate modeling language, right? Everything is math. You can't get away from it. So, compute a loan amortization table. The way that a loan works is you go to the bank and you say, I need to buy a car. That car is, say, $10,000. It's a used car. And I'm going to take out a 5-year loan. 12 months in a year, that's 60 months. And it's a 5% interest loan. Right? In other words, we're going to make 60 payments, but we're going to be paying the bank back each month, but we're also going to be paying them interest, 5% annual interest. And the way that comes out is that the monthly payment formula is the rate times the principal. So in other words, 5% divided by 12 because it's a monthly thing, right? You pay out by the month. If you were paying every day, you would divide this by 365. If you were paying once a year, you divide it by 1, right? Loans don't usually work that way. So that's the monthly rate, right? Times the principal, $10,000. 1 minus 1 plus the rate raised to this negative n, where n is the number of payments that you make. That gives you a monthly payment. In this case, it's $188.71. But you have to be careful here. Right? This math here will not work out to a whole cent necessarily. So what you need to do is you need to round to the nearest cent. Right? And that will give you your monthly payment. Now, the way that it works is in the first month, you've got $10,000 that you owe the bank. Then we compute the interest that month that you owe. Where did we get that number? That was the monthly rate times the current principal. So, Mr. Wolfram Alpha, tell us what that is. 0.05, that's 5%, divided by 12, times 10,000. That's $41.66.66666. What do we do with that? We round it, and we get $41.67, which is that number right there. Now, our monthly payment was $188.71, minus the amount that we have to pay the bank for interest, gives us $147.04 that we're actually paying the loan down, right? That means that the new balance ends up being $10,000 minus this, the amount that we actually pay towards principal, giving us $9,852.96 at the end of the first month. That feeds into the next month, in which this monthly interest rate is recomputed because we have a new balance. We are paying more towards that principal that month, and so we're paying down this loan month by month by month. The amount that we pay it down, though, by grows because the amount of interest that we pay actually shrinks. This is where the term amortization comes from. You don't actually pay 5%. You pay something slightly less than 5% because you're paying it down each month. Right? Now, if you have a loan that you don't pay, right, then the interest accrues. You start paying actually more because then it compounds. You don't want to do that. Any questions on how this works? All right. Then let's go ahead and write it up. So I'm going to need some inputs here. The inputs that we read from the user, or that we're going to hard code here, are the rate. N is the number of periods, the number or years, we could say, and the original principal. So let me go ahead and call those things, I don't know, double R for rate, P for principal, and Y for years. Are those good variable names? Nope. Write 10 lines of code, and what was P again? Right. Payment? Nope. What was it? Principal. So here's the rate, and we'll go ahead and hard code that to be 0.05%. Our principal, right, it's principal, not principal, right, is $10,000. Oh, I've seen this mistake several times. Is that correct? Can you use commas in literals in either programming language? Nope. It came up with if-else-if statements. If x is less than 10,000 and y is greater than, I don't know, 1,100, right? Then we did something. It compiles, it runs. It's probably not going to work for all inputs, right? Why does it compile? Because this is just a simple, I believe, a disjunction, but don't quote me on that. I forget what it is. If this ends up being 0, 0, 0, then this ends up being, is it the case that x is less than 10 or false and y is greater than 1 or true? That's not what we mean, right? So, no, you cannot use commas. It'd be nice if you could, but I don't know of any programming language that lets you do something like that. The only reason that we use commas in like written numbers is to break it up, right? Thousands, millions, billions, right? It makes it easier to read. Right? Rate and years is equal to 5 years. Oh, wait a second. Rate, certainly, that's going to be 5%. That's a floating point number. I could take out a loan for $10,000.50 if I wanted to. right? But years, you could have a loan, I guess, for 5.5 years, but that's not really how it works, right? You usually take it out for a fixed number of years. What's a better, more appropriate variable type in this case? An int. Okay. Now, my first order of business here is to compute the monthly payment. Right? So let's go ahead and do that. Double, and I'm going to use good variable names from now on. Monthly payment is equal to, and it's just going to be a translation of this formula up here. Right? The rate, remember, divided by 12 times the principal, right? Divided by 1 minus 1 plus rate divided by 12, 12 raised to the negative n. Right? Help me troubleshoot that. If we want to, we can look at the example right here. Right? The rate divided by 12 times 10,000, that's my numerator. There we go. My denominator is going to be 1 minus 1 plus the rate. Again, it's going to be divided by 12, raised to the negative n. Well, can I do that? Nope. What do I have to do? Power, right? Raised to the negative n, that matches that, and then there's the end of my numerator. There we go. Okay. You can put negations in front of variable names. That's perfectly fine. Do you see an n anywhere here? Nope. So I probably want that. Except that, what does n represent again? N is the total number of periods, months, in the loan. So should I call it n when I know what it represents? Months. Right? Or terms, or whatever, right? And it's going to be the years times, we all know how many months are in a year, right? 12. There we go. And I will put in months over here. Okay. So ad hoc testing. Let's test as we go to make sure that we're not writing 100 lines of code and then having to go from top to bottom to deal with bugs. Printf. Monthly payment is going to be dollars because this is currency. And it's going to be %f and the line. Monthly payment. There we go. GCC. This is still demo. Let me bring this back up here now. And same warnings as before. We ignore those. A dot out. $188.71 and nearly a quarter cent. Right? Well, that looks kind of almost right. What did we forget to do? Round it to the nearest cent. Monthly payment is equal to round to the nearest cent monthly payment. Do you think that there's such a function? No. It'd be nice if there were, right? It'd be really nice if the math library just had that for us. Well, if you ever find yourself wishing like a Christmas list or something like that, I really wish that function existed. Write it, right? Write that function and put it into your own library. You can't put that into the math library, but you could use the math library, start writing your own functions, start creating your own libraries, and that's what we're going to be doing next. For now, though, how do I round to the nearest cent? I have to use the math library's round, but that will only round it to $189. So what was our trick for rounding to the nearest cent? Multiply by 100 and then fix it by dividing by 100 after the rounding. Let's see if that still works. It works now. Looks good. Now it's $188.71 exactly. Except that we shouldn't be printing it like that. I'll only print it out to the nearest cent. 2 decimal places of printing. All right, great. Now we've set ourselves up for, I don't know why I jumped down there, but now we've set ourselves up to build this loan amortization table. Obviously, I'm going to print out the month, the balance, the interest, and the new balance. So let me go ahead and take care of that immediately, printf. We'll worry about alignment and making it look pretty later. Right. Month, balance, interest, new balance. So there are 4 things that I'm going to print out every single iteration of this. What kind of a loop does this suggest to you? If it's 60 months, you're going to be going how many lines here? And I didn't put all 60 months here. Hopefully that's clear. Because the bank doesn't let you quit paying after only 6 months when you still owe $9,180. That'd be very nice if they did, right? So ... I just cut it off. So what kind of a loop do we want to use? 4, because I know exactly how many iterations I'm going to go here. And I'm going to take a departure from our usual idiomatic for loop. Instead of I'm going to say month. My months, however, start at 1. While a month is less than or equal to months, right? That's why I pluralized it. Month plus plus. Because I want to print out that month. Printf, %d, end line, month. Now that's only going to print out the months. 1, 2, 3, 4, all the way up to 60. If you want to, you can test that. There you go. That works. But now what do I need? I need to print out the current balance, the amount of interest that I'm paying that month, the amount of principal that I'm paying that month, right? And then the new balance that actually gets results after that, after making that principal payment. So how many variables am I going to probably want here? Double. Monthly, a month. I can't say monthly interest because it changes every month, but I could call it month's interest. How much is that? It's the rate divided by 12 times the principal. That seems fishy, but whatever, right? Okay. Now, double principal payment, right, is going to be the monthly payment minus that month's interest, right? So I've got 2 of the 4 things. I've got my principal, right, the balance, and then the new balance, double new balance. Oops. Balance will be equal to the principal minus the principal payment. There we go. And now let's print those things out. %f, 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 %f. 4 things, right? 1, 2, 3, 4. Yep. So there's the month, the principal, the month's interest, the principal payment, and then the new balance. Okay. Put $sign. I'm not going to worry about the formatting just yet. I want to make sure that this is working. Right? All right. Looks like it's okay. At least it compiles. Run it. 60 months. Uh-oh. Do the numbers ever change? Nope. So help me out. What's the issue? That first month's interest looks okay, but okay. What's wrong with 41.66? Should be 41.67, right? What do I need to do there? Round to the nearest cent. Man, if we had that round to the nearest cent, I wouldn't have to write this over and over and over again, right? If I'm using the same piece of code over and over and over again, that's not repeated like a loop, that should be screaming out to you, make a function, right? And reuse that function. Principal payment, probably don't have to round that, because if both the month's interest and the monthly payment are both rounded to the nearest cent, then then their difference is going to be rounded to the nearest cent too. Okay? The new balance is the principal minus the principal amount. Is that how we worked it out in this table? The new balance fed into the next month. The new balance fed into the next month. We're changing the balance, right? The principal is the original amount that we borrowed from the bank. As we pay it down, that's referred to as the balance. Double balance is equal to principal. There we go. Initially, it will be the principal, but after the first month of payments, it's different, right? The new balance is going to be the balance minus the principal payment. Let's try that. All right, looks like everything is rounded, so I'm going to go back and reformat all this stuff. Right? Dollar signs, 0.2, dollar sign, 0.2, dollar sign, 0.2. But it still is not changing. That first month seems correct, right? 9,852.96 cents. 9,852.96 cents. That second month is not. We've got a balance and a new balance. Much like the arithmetic geometric mean, what do we need to do? Here's the old balance, the current balance. Here's the new balance. What do we need to do? We need to shift it so that the new balance becomes the current balance. Right? Where should I do that? Should I do it? Let's do it immediately. The balance will become the new balance. Got to spell it right, though. All right. Okay, so we're changing definitely here, except that we should no longer be printing the principal. We should be printing the balance, the current balance. Sorry, that's another change I meant to make. There we go. All right, so we're getting somewhere, right? We're not nearly there yet, though. Okay. Yeah, go ahead. Oh, up here or? Up here? There we go. Balance is equal to the principal. That's before the process starts. So what's my bug here? In the first month, I shouldn't be printing the new balance. What should I be printing? The current balance, the old balance. So let's wait to update that until we get down here. Okay. GCC this and run it. Okay. Good. $10,041.61. 147.04. That works. Excuse me. 98.52.96. 98.256. 41.05. Okay, so there's where we fail. Right. The interest is never changing. The interest is not based on how much money you originally borrow. It's based on how much money you still owe. But what did we do? We used the principal instead of the balance, which is what we should have used. All right, fix. All right. Go. All right. Oh, wow. That looks really good, because at the last month here, we only have 14 cents left. Right. So it looks like we're almost paying that off. And by the way, in real life, if you ever do have a loan and you pay it early or something like that, and in the last month you only owe 14 cents, don't bother paying it. They forgive it. I think the rule is if it's less than $1, they don't even bother. Sometimes in some cases, if it's less than $5, they don't. But in any case, we've got that looks good. That looks good. We only have our test case out here to the 6th month. 9, 2, 5, 8, 6, 7. 925, or 63, excuse me, 38, 59, 50, 13, and 91. Oh, okay. I'm convinced, at least given this input, that everything is correct. So why do we still owe 14 cents at the end of the day? Because of all those rounding issues, right? And that's how loans work, right? If we wanted to, what would to make this absolutely accurate and get it down to zero balance, what would we have to do? We would have to take care of that last month separately, right? Just like those the Zune bug and a bunch of other bugs that we've seen. If you're off by one, either the first iteration is wrong or maybe the last iteration is wrong. It's very or every iteration is wrong. It's almost never the case that all of them are right except for that 58th iteration, right? That sounds so weird, right? Yeah.
How'd you get yours to stop at 14 cents? Mine's kept going down on negative numbers.
I don't know. Do you have a for loop?
No.
I would say probably your monthly payment is too high then. Unless, did you print that out and verify it? Your monthly payment should be $188.71. My guess is that it's greater than that and you end up paying more and more. But in any case, the last month here, let's go ahead and deal with that by itself, right? The month's interest, the principal payment, the new balance, we probably have to deal with that last iteration by itself. But we only have a few minutes here, so I'm not going to do it. Instead, like every good programmer, what am I going to do? To do. Handle the last month separately. I'm going to put in a to do here so that I remind myself that I need to do it. And then I'm going to be lazy and I'm going to do it later. I'm going to procrastinate until it's absolutely necessary. If you do something like that over here in Eclipse, I'll show you what not the consequences are, but the nice thing about this is to do. It's not green anymore, right? It's highlighted in blue. Do something here. It's a comment, so it is ignored by the compiler, it is ignored by the language, but guess what? Your Eclipse will pick that up as a task that needs to be done. Right? Now, I've got a whole bunch of other projects over here, but what you can do is, what is this, 155H, and it's spring, or it's fall. Fall 155H. Where are we? Got a lot of things I need to do apparently. Oh, there it is. Nope, that's not it. Darn it. Anyway, I'll just show this to you. That you can double click on it and it'll open the source code where you've got this to do there. Right? And this is just a list of tasks. It gathers them all here. And so it's just a little helpful tool that you can use in your IDE. I am sure that VS Code supports that in some way. I don't see it here, but the full VS Code desktop might do something like that. So if you're ever, I need to take a break, or something is interrupting me, or whatever, make sure that you're putting a to-do there as a reminder that you need to come back and fix that. All right, we'll continue next time with some actual unit testing.